Let us look at proposition number 23 of book 11 of Euclid's Elements. The proposition says to construct a solid angle out of three plane angles such that the sum of any two is greater than the remaining one. Thus, the sum of three angles must be less than four right angles. Okay. Now, in the previous proposition, we have already seen how to construct a triangle using AC, DF, and GK. So we will not get into that. So, which means that those conditions are already satisfied. What are the conditions? That sum of any two of these angles is greater than the third, and the sum of these three angles is less than four right angles. So now let's construct the triangle first. So let's take a point and let's draw ML equal to AC. Again, MN will be equal to DF and NL will be equal to GK. So that we end up with a triangle. What we have to do is circumscribe a circle on this triangle. That means we have to draw a circle which passes through L, M, and N points. We know how to do that. Take the midpoint of these three sides, draw a perpendicular to NL from O. Similarly, perpendicular line to ML. And actually that is enough, but just to be sure, we can draw the perpendicular to MN as well. Now, using this as the center, the intersection point of these three lines, we can draw a circle with the radius as the center to either L, M, or N. And it will pass through these points L, M, and N. So now let's mark the center point as O. And let's get rid of these elements. Now here, OL, OM, and NO, they will all be equal. Why? Because they are all radii of the same circle. Now what we have to do is construct a line perpendicular to the plane in which LMN are. So let's draw that perpendicular. Now this is perpendicular. If I move it, it becomes much more clearer that it is perpendicular to the plane of LMN. Now, on this perpendicular line, we have to find a point based on a condition. And what is the condition? That let's say this is R. The square on OR should be equal to the square on AB minus the square on OL. Based on that condition, we have to mark this point on this line. This OR, the square on that is equal to the square on AB minus the square on OL, which means that the square on AB has to be greater than the square on OL. Otherwise, subtraction will give you negative length, which is not allowed. So, which means AB has to be greater than OL. Now we can prove that AB is greater than OL by using contradictions. So first let's assume that AB is equal to OL. Now if AB is equal to OL and ML is equal to AC, then what happens? Because OM is also equal to BC. Because remember, we are given that AB is equal to BC and OM is equal to OL and ML is equal to AC. So which means side, side, side. Using that proposition, we can say that these two triangles are congruent. Triangle ABC and LOM. Similarly, we can prove for the other two triangles also. That triangle DEF is equal to MON. Triangle GHK is congruent to NOL triangle. But that means what? These three angles added together will give us 4 right angles. And because of this equality, sum of these angles is equal to sum of these angles. So since the sum of these three angles is 4 right angles, the sum of these three will also be 4 right angles, which is against our proposition that these sum of these three angles is less than 4 right angles. So which means AB cannot be equal to OL. Now, the other case is what? That AB is less than LO. Let's do one thing. Let's mark a point on OL. Let's say let's mark a point P, and let's mark a point Q, and let's join these two. Let's say OP is equal to AB, which means OQ will also be equal to BC. Now we join PQ. AB is equal to BC. OP is equal to OQ, which implies LP is equal to QM. Therefore, LM is parallel to PQ, and the triangle LOM is equiangular with POQ triangle. That means we can build proportionalities. OL is to LM is equal to OP is to PQ. Or alternately, we can say OL is to OP is equal to LM is to PQ. Now, LO is greater than OP. Because of the proportionality, we can say LM is greater than PQ. But LM is equal to AC. That means AC is greater than PQ. Since AC is greater than PQ, that means angle ABC is greater than POQ. Or we can also say ABC is greater than LOM. Similarly, we can show in all the other two triangles as well. So if we take angle LOM, MON, and NOL, if we add them up, we get 4 right angles. And since we have said angle ABC is greater than POQ, that is LOM, that means DEF is greater than MON, and GHK is greater than NOL. So if we add up these angles, this becomes 4 right angles, but the sum of these 3 angles becomes greater than 4 right angles, which is against the proposition which says that the sum of these three is less than 4 right angles. So which means AB cannot be less than LO, and it is not equal to LO. That means the only possibility is that AB is greater than LO. Now the reason, as I mentioned previously, that AB has to be greater than OL is because we are subtracting the square on OL from the square on AB. And we have proved that yes, AB is greater than OL. So let's hide off all these which we don't require. And now we join RN, RM, and RL. RO is perpendicular to the plane of LMN. That means it is perpendicular to MO, LO, and NO. LO is equal to MO and NO. Now we have to prove that these angles, angle LRM is equal to ABC, MRN is equal to DEF, and NRL is equal to GHK. So let's see how we can prove that. Now RO is perpendicular to each of is perpendicular to the plane of LMN, and LO is equal to MO. OR is common. So that means triangle LOR is congruent to triangle MOR, which implies RL is equal to RM. Similarly, we can show that RN is equal to RM. So what it means is that RL is equal to RM is equal to RN. And since OR square is equal to AB square minus OL square, using Pythagoras theorem, we can understand that if OR square is equal to AB square minus OL square, that means AB square is equal to OL square plus OR square. But RL square is also equal to OR square plus OL square, which means AB square is equal to RL square, which means AB is equal to RL. Now, remember AB is equal to BC is equal to DE is equal to EF is equal to GH is equal to HK. And now we have shown that RL is equal to MR is equal to RN. And we have shown that AB is equal to RL. That means LR is equal to AB, RM is equal to BC, and LM is equal to AC. That means triangle LRM is congruent to ABC. Because of that congruency, we can say angle ABC is equal to LRM. Similarly, we can show that angle DEF is equal to MRN. And similarly, we can show that angle GHK is equal to NRL. So we have constructed a solid angle based on three plane angles, such that the sum of any two is greater than the remaining one, and the sum of three angles are less than four right angles. So that is proposition number 23 of book 11 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.